Hello everyone, welcome to another video of Calculus 1. In a previous video, we learned that how to find the behavior of function, particularly whether the function is increasing or decreasing, increasing or decreasing based on the first derivative. If you have a function f of x, uh, and if its first derivative, f prime of x, is greater than 0, then for some region where x is in interval AB, then f is increasing. Now, if f prime of x is less than 0, then in the region in the interval AB, f is decreasing. And then we also learned that when the sign of f prime of x changes from positive to negative around a critical point, right? We can find the critical points if f prime of x is equal to 0 or f prime of x does not exist. We can find the critical points. So once you find the critical points, we can see that how the sign of f prime of x changes around the critical point, and we can say whether that around the critical point, if that critical point is a minimum, local minimum, or local maximum, right? If sign changes from positive to negative, that's called local maximum. If the sign of f prime of x changes from negative to positive, that's called local minimum. That's called local minimum. Now in this lesson, in this video, I'm going to introduce you the second derivative test. Second derivative test. Now, let's see what the second derivative test and how we're going to use that to see whether the function is concaving up or concaving down uh, in a certain region of the domain, a certain interval of a domain. So first, we go to this page. Uh, the second derivative test, we look at a function. Uh, in this case, we're going to look at a function that concaves up, f of x, this is x. Now we're going to look at uh, f prime of x. F prime of x is a tangent to the curve at different places. So we have tangent to this curve here and tangent to this curve at this point and tangent to the curve at this point. And you can see that the slope of the tangent line here is negative. So that means the sign of f prime x is less than 0, and the sign of and the value of f prime of x is 0 here because it's a flat. And in this case, the slope of the tangent line is f prime of x is positive, right? So with that, we can draw the curve or see how the sign changes of f double prime x or f prime x here. So if I draw f prime x against x, first it was negative, some value negative, and it gradually becomes 0 and then goes to positive. Now if you consider this graph, and if I draw a tangent to this curve, which represents f double prime of x. The slope of this tangent line represents f double prime of x. Now the slope in this case, is positive. So this angle is this tangent of that angle is positive. So that means f double prime of x is positive. Now you see that when f double prime of x is positive, if you calculate the f double prime of x, and at a certain point, if you find uh, the sign of f double prime x, you can see that the function is concaving up. Let's consider the other instance where function is concaving down. We can do a similar graphical analysis. Now I can draw the tangent lines at different locations. Here's the tangent line. The slope of the tangent line is positive. That is f prime of x is positive. And then f prime of x is 0 at this point. And then this point f prime of x is negative. Now again, I'm going back to the curve of f prime of x. If I draw the curve of f prime of x here, initially it was positive. It was positive, and then gradually becomes negative, right? And if I draw a tangent line to this curve, you can see that the slope of this tangent line is negative. So that means f double prime of x is less than 0. That means for functions that are concaving down. So if it is concaving down, you will see a negative f double prime of x. And if it's concaving up in a certain region, you see a positive f double prime of x. So, and also we can say that f prime of x, what happened to f prime of x? F prime of x is increasing when it is concaving up. And when it is concaving down, f prime of x is decreasing. So, if f is concaving up, f prime of x increasing. See this graph, f prime of x, this graph is f prime of x, this blue curve. It is increasing, starting with negative, becomes 0, increasing, and goes to higher values. But f double prime of x is positive, right? Concave up, then this f double prime of x is greater than 0, concaving up case, right? And let's look at the f is concave down. f prime of x, f prime of x is decreasing. So this function, you'll see f prime of x is decreasing. And the slope of the tangent line drawn to the f prime of x, the curve of f prime of x, that is f double prime of x, is negative. So you can see that here, this is decreasing, but f double prime of x less than 0 for concaving down case. Now, we can, by looking at f prime of x and f double prime of x, we can easily figure out um, what happened to a function, whether the function is concave up or concave down. Now, we sometimes have situations where the functions start with either concaving down and then turns back and go like concaving up. So we have a kind of a inflection point, and also we can have concaving up and then concaving down. So this is also inflection point. These points are called points of inflections. Points of inflection. Well, what's really happening here? It's concaving down. We learned that if it is concaving down, that is f prime of x is decreasing and f double prime of x is negative. So this is f double prime x is negative. And when concaving up, after the inflection point, f double prime x is positive. And here, if it is concaving up and concaving down curve, f double prime of x is positive here, and f double prime of x is negative here. So what we can see is that around the inflection point, the sign of f double prime x changes. Around an inflection point, the sign of f double prime x changes. F double prime x changes. And we can also figure out that. Now, let's analyze this problem in a graph, okay? In a graph. So let's say we have a graph that has an inflection point concaving down and concaving up. And right here you have an inflection point. So let's see what happened to the slope of the tangent to the curve, right? The slope of the tangent to the curve is positive here, is negative here, and is positive here, and then it becomes, so it's negative here, right? And becomes 0 here, and then become positive here, right? So we have positive goes back to 0 and become negative and goes back to 0 and come up again, right? Uh, that's how we can draw our prime of x. Let's see how we're going to draw the function of f prime of x. So we have f prime of x on the y-axis and x on the x-axis. So we can see that the f prime of x start with positive and becomes 0 and then goes to negative and then gradually reduces by negative and becomes 0 again and becomes positive. So we have a function start with negative, function is start with positive, coming back and then becomes 0 right here. And then what happen is from here it start again to turn back and goes back to 0 and then positive. So at this point you have a 0, that is this point right here. Let me draw it, this point. And then up this point right here, you have another 0. These are the points that correspond to the f prime of x0. And the curve of f prime of x, the tangent drawn to the curve of f prime of x is f double prime of x. So you draw f double prime of x tangent to these curves, that becomes f double prime of x. Now you can see that at this place it is negative, in this place it is positive, the slope, and here it is negative, and here it is 0. And at this point where you have a flat uh, slope, that means 0 slope, that means 0 f double prime of x. So you have f double prime of x, x0 at a inflection point. Now that's only one condition, and you can see that the sign around the inflection point, f double prime of x less than 0 here, and f double prime of x greater than here. So sign around the sign of f double prime of x changes, right? The sign of f double prime of x changes. So if f double prime of x0 at a certain point and the sign of f double prime of x before the point and the after the point changes, that's going to be an inflection point. And then also you could have another instant where there's an inflection point. So if we have inflection points something like this is also called an inflection point, where we have a condition that the derivative, the first derivative f prime of x against 0. But now if f prime of x is positive here, uh, and again it is positive here as well, right? And now let's see, this is a special case. So we have a condition where f prime of x is positive, right? You have f prime of x in this case is positive. So you have a positive value for f prime of x. You have f prime of x here. You have a positive value. You have a positive value. It's positive. It could happen like that. And goes to 0, goes to 0. And then it becomes positive again, right? Come to 0 right there. That's the inflection point. That's the corresponding inflection point, and goes back to 0. And what happened to f double prime of x? F double prime of x again, f double prime of x is sign less than 0. And here f double prime of x is greater than 0. The sign of f double prime of x changes. But what happened to f double prime of x at this point? Let's say this is point C, right? At point C, f double prime of x, C, does not exist, right? F double prime of x is not does not exist in this point, right? So we have two situations where we have inflection points. So either f double prime of x is 0, or f double prime of x does not exist, but the sign of f double prime x should change in either case, right? So let's summarize what we learned now. We learned for functions that are concaving up, concaving, concave up functions, the sign of f double prime of x, right? Concaving up functions, uh, the sign of f double prime of x is greater than 0, and when concaving down, the sign of f double prime x is less than 0, right? And if at x equals c, f double prime c is 0, or f double prime c does not exist, and f double prime of x before and after x equals c, the sign, let me say, the sign of f double prime x before and after x equals c changes, then x equals c is a point of inflection, is a point of inflection. So, and then we can get some information from f prime x as well. F prime of x, when it is uh, concaving up, f prime of x increasing, and when it's concaving down, f prime of x is decreasing. Okay, so with this information, we can actually find whether we have a local maximum or local minimum at x equals c. Now let's say whether we have a local maximum at x equals c. That's a concaving up case. In that case, we have a negative value for f double prime of x. If it is concaving up, that's you have a minimum function that f double prime of x is uh, greater than 0. But when f double prime x is 0, uh, it is inconclusive. It may be a local minimum or local maximum or neither. But if double prime of x 0 and the sign of f double prime of x changes, that could be an inflection point, right? So to summarize at the end, right? If f double prime c greater than 0, fc is local minimum. If f double prime c less than 0, fc is local maximum. F double prime c is less than 0, inconclusive. Either could be local minimum or maximum, but if double prime of c is 0 and or if double prime of xc does not exist, either or this, right? Uh, and if double prime x changes the sign at x equals c, then it's an inflection point. It's an inflection point. So let's take an example. Find the points of inflection uh, f of x for function f of x equals 3x to the power 5 minus 5x to the power 4 plus 1. We can find f prime of x first, which is 15x to the power 4 minus 20x to the power 3. And you can also find f double prime of x, which is 60x to the power 3 minus 60x squared. And we can find the points where f double prime of x is equal to 0. Those are inflection points, but we shouldn't come to the conclusion until we figure out whether what happened to the sign of f double prime of x around those points. So we'll find where f double prime of x 0, 60 x cubed minus 60x squared equals 0. So you can factor out 60x squared, that's equal to x minus 1 equals 0. So at x equal 1, f double prime of x equals 0. So this could be an inflection point. But let's see. So we have 1, negative infinity to positive infinity, and that's 1. So we divide into two regions, negative infinity to 1 and 1 to, x equals 0 is also another point, right? X equal 1 and x equals 0, f prime of x equals 0, right? So you have negative infinity to 0, 0 to 1, and then 1 to positive infinity. Those are three regions, right? So when this is the expression that we need to find the sign x squared x minus 1, right? So if you put any number less than 0, let's put negative 1. So this is positive. When you put negative 1, this term is positive because it's positive. But this term, if you put negative 1 minus 1 is negative 2. So you have positive. So you have positive times negative, which is actually negative, right? So if f double prime of x, right, this is f double prime of x, and the sign of f double prime of x is negative. The sign of f double prime of x negative means you have the sign of f double prime of x is negative means it's concaving up, right? So you have concave up. And then the second case is 0 to 1. Let's put zero point 0.5, right? Let's put 0.5. 0.5, if you consider the first term right here, it's x squared, it's positive. And the second term, 0.5 minus 1, that's going to be minus 0.5, right? Minus 0.5, that is negative. So you have a negative case here. So that means concave up. Okay, now we have concave up and then concave up. And then we can find uh, a number which is greater than 1. Let's find 2. Number 2, the first term here is positive anyway. When you put 2, this number is also positive. The positive times positive times positive is positive. That means concave down, concave up, concave up, concave down. Now we have change in sign, change in sign of f double prime of x, right? But and then also f1, f double prime of 1 is equal to 0, and change the sign. That means it is a 1, and if you substitute 1 to f of x, that's going to be, this is 3, 3 minus 5 is minus 2, negative 2, negative 2 plus 1 is negative 1. So 1 minus 1, 1 minus 1 is an inflection point. It's an inflection point. So 1 minus 1 is an inflection point. We know that at x equals 0 also, if double prime 0 is 0, but the sign of f double prime 1, f double prime x at x equal 0 does not change. So it is not an inflection point. It is not an inflection point. So that we found all the inflection points. Uh, yeah. And sometimes, as I explained earlier, there could be instances where the second derivative does not exist. But even in that case, if you find the changing sign of f double prime of x, then that point would become a uh, inflection point. So, and then also we figured that for critical points, right? For critical points, f double prime of x tells you whether it is a local minimum or local maximum. Now, what are the critical points of this function? So, if you want to find the critical points, that means where that if prime of x is 0, right? Those are the critical points. And also places where f prime of x f prime of x does not exist, right? Those are the critical points. So let's find the critical points, right? 0 or f prime of x does not exist. So you have f of x, which is equal to, in here this case, 15, sorry, 3 x to the power 5 minus 5 x to the power 4 plus 1. So f double prime of x is 15 x to the power 4 minus 20 x to the power 3. So if you equal this to 0, that you get 15 x to the power 4 minus 20 x to the power 3 equals 0. So you can put 5 times x to the power x cube equals times 3x minus 4 equals 0. So x equals 0 or x equal 4 over 3 are critical points. Critical points. Now at critical points, we can find f double prime. So f double prime of x, we got previously 60x cubed times x minus 1. Now when x equals 0, f double prime 0 is 0. So in this case, we have inconclusive at x equals 0. And then when x equal 4 over 3, f double prime 4 over 3 is equal to 60 times 4 over 3 cube 4 over 3 minus 1. So this number is anyway positive, but this number is also positive because it's greater than 1. Positive, positive. So this becomes what? This is a positive number. So f double prime, it's a local minimum. It's a local minimum, right? So we figured that at x equal 4 over 3, there's a local minimum. And at x equal 1, we figured out at x equal 1, there is a inflection point. So you have x equal 1 inflection point. There's an inflection point. So these are the conclusions that we can make with the information that we have about this function. So we have a point of inflection at x equal 1, and there's a point of inflection. We cannot say that there's a point of inflection at x equal 0 because it is not conclusive. We cannot say that. There may be, it's inconclusive. And you have this f double prime of x, f double prime 0 is 0, that is inconclusive case. But you have a local minimum at x equal 3 over 4. We have a local minimum at x equal 4 over 3. 4 over 3. So that's about that example. And yeah, sometimes the second derivative test would become inconclusive, as we showed earlier. And let's take another example. So we have f of x equals x to the power 5 minus 5 x to the power 4. Analyze critical points. So first we find f prime of x. That's going to be 5 times x to the power 4 minus 20 times x to the power 3. So if I take from this, that's 5 times x to the power 3 times x minus 4 then f double prime of x is 20 x to the power 3 minus 60 x squared. Take 20 x squared, this is going to be x minus 3. So critical points, if f prime c equals 0 or f prime c does not exist, x equals c is a critical point. So we make it that is 0, f cube, that is actually f prime of x minus times x minus 4 equals 0. From that we get x equals 0 or at x equal 4. These are the critical points. And we can use the second derivative test. If f double prime c greater than 0, local minimum, greater than 0, local minimum. If double prime c less than 0, local maximum. If double prime c equals 0, inconclusive test. So let's find those two critical points at x equals 0. If double prime 0 equal to 20, 0, 0 minus 3, which is actually 0. So this case it is inconclusive. And at x equal 4, f double prime 4 is equal to 20 times 4 squared, 4 minus 3, that is 1. 4 squared is 16, 16 times 20 is 320. 320 is greater than 0, that means it's a local minimum. At x equal 4, local minimum. So when x equal 4, f4 is 4 to the power 5 minus 5 times 20 times 4 cube, right? So that point is we do a calculation that will become, let me find it out. It's negative 256, right? So we have negative 256. That's the value of that. So we have 4 negative 256 point is local minimum. Local minimum. And at x equal 0, it's negative. It's an inconclusive derivative test. So we have 2 points. That's actually 0 and 4. At 4, we know that it's a local minimum. And let's look at the sign of f prime of x. So we can find the f prime of x, which is x cube times x minus 4. So we have x5 x cubed times x minus 4. So if you put a value in between 0 and negative infinity, let's put -1. So if you put -1, this is negative, and this is also negative. So negative times negative, that is positive. That's f prime of x is positive. And then if you put a value higher than 0, let's put 1, this is positive, but that's negative. So that is negative f prime of x. So the value of f prime of x changes from positive to negative, changes from positive to negative. That means it's a local minimum. At x equals 0, you have changes from positive to negative. So you have positive to negative. So that's actually local maximum. Sorry, it's a local maximum. So this point is local maximum. This point is local minimum. If f double prime of x is 0, if double prime of x 0, that means at x equals 0 and x equals 3, that's an inflection point, right? So 3 is here. That's a point of inflection. But we have to find whether uh, there could be a point of inflection, but we have to find the sign of f double prime of x at x equals 3. So sign of f double prime of x, if you put f double prime of x, that is x squared, 20x squared, x minus 3. If you put any value uh, less than 3, this is always positive. Less than 3, then this is going to be negative. So that sign is negative here. F double prime of x. F double prime is negative. And if you put anything higher than f double prime of x is positive. So that's a point of inflection. X equal 3, point of inflection. X equal 3 is point of inflection. So this is how we find the points of inflections, local maximum, local minimum, by using the first derivative test and second derivative test. With that, I would conclude this video. Thank you very much for listening.